Reality is not what it seems. Beneath everything you see and touch lies a hidden architecture of invisible forces, the universe's secret fields. These are not just abstract ideas. They are the fundamental frameworks that dictate how particles get their mass, why the cosmos expands, and what the fabric of space-time is truly made of. By the end of this journey, you will understand 30 profound theories that reveal a cosmos far stranger and more interconnected than you ever imagined. We will explore why time might flow like a river, and if the vacuum of space is actually bursting with phantom energy. What single mystery about the universe keeps you awake at night? Our universe is held together by an invisible ocean. This is the Higgs Field, an energy field that stretches across every inch of space, completely unseen yet absolutely essential for our existence. Without it, you, me, and everything we know would simply not be here. The theory of the Higgs field answers one of physics' most fundamental questions: why do things have mass? The idea is that particles are not inherently heavy. Instead, they acquire mass by moving through this cosmic molasses, this Higgs field. The more a particle interacts with this field, the more it slows down and gains what we perceive as mass. Think of a famous celebrity trying to walk through a crowded room. They interact with the crowd, slowing them down, making their movement feel heavy. A particle like an electron barely interacts, slipping through the crowd with ease and possessing very little mass. But a top quark, one of the heaviest known particles, would be mobbed, struggling to move at all. This elegant idea needed proof, and it came from one of the most ambitious scientific experiments ever built. Deep beneath the border of France and Switzerland, the Large Hadron Collider at CERN smashed protons together at nearly the speed of light. Scientists were hunting for a ripple in the Higgs field, a telltale particle that would confirm its existence. In 2012, they announced their historic discovery, the Higgs boson. This was not just finding another particle, it was the moment we confirmed the existence of the cosmic ocean itself, validating the final piece of the standard model of particle physics. Now consider a universe where this field is switched off. In that stark reality, particles would feel no resistance. They would all travel at the speed of light, massless and forever free. There would be no clumping together to form atoms, no stars, no planets, and certainly no life. The cosmos would be a silent, featureless sea of radiation, a flash of light without any substance. The Higgs field is the universe's great sculptor, giving form to the formless and substance to the void. But the Higgs field is not the only invisible sculptor of our reality. Another, far more powerful field is thought to have orchestrated the very birth of the cosmos in its first fleeting moments. This is the Inflaton Field, a hypothetical energy field that may have put the bang in the Big Bang. In the beginning, the universe was unimaginably small, hot, and dense. Then, in a fraction of a second so brief it defies comprehension, it exploded in size, expanding faster than the speed of light itself. This was the epoch of cosmic inflation, a violent growth spurt driven by the Inflaton Field. Think of the universe as a tiny patch of fabric, wrinkled and tangled. The Inflaton Field acted like a cosmic iron, smoothing out every wrinkle and stretching that fabric to an incredible, almost perfectly flat sheet. This single idea solves two of cosmology's greatest puzzles. The horizon problem asks why the universe looks the same in all directions. How could regions now billions of light years apart ever have been in contact to even out their temperature? Inflation answers this by stating they were once neighbors, pushed apart by that sudden, faster-than-light expansion. The flatness problem asks why the geometry of our universe is so perfectly balanced, like a pencil standing on its tip. Inflation explains that the immense stretching forced the cosmos into this precise, flat geometry. We have evidence for this incredible event imprinted on the sky. The cosmic microwave background radiation, the faint afterglow of the Big Bang, shows tiny temperature variations. These are the quantum seeds, the microscopic wrinkles that were magnified by inflation into the vast cosmic web of galaxies and voids we see today. The Inflaton Field is the ultimate creative force. Its energy drove the universe's explosive birth, and its eventual decay is believed to have filled the cosmos with the hot plasma of particles that would eventually become everything we see. The field itself then vanished, its job complete, yet its ghostly fingerprint remains etched into the oldest light in the universe, a permanent record of our cosmic dawn. The hunt is now on to understand the true nature of this elusive field. What particle was it made of? What made it start its roll down that energy hill, and what made it stop? The answers are hidden in the subtle patterns of the cosmic microwave background, waiting for the next generation of telescopes to decode. That creative burst of inflation ended, but the vacuum of space did not fall silent. Empty space is not truly empty. It is a seething, bubbling sea of quantum activity governed by fields that never rest. This is the realm of quantum fields and vacuum energy, a hidden layer of reality that might hold the key to the universe's ultimate fate. Every point in space is home to a collection of invisible fields, one for every type of fundamental particle. Even when you look at a perfect vacuum, a region with no particles at all, these fields are still there, vibrating with a fundamental energy. This is the zero-point energy, the lowest possible energy a quantum system can have, and it is not zero. This energy gives rise to one of the strangest phenomena in physics, virtual particles. Governed by the Heisenberg uncertainty principle, which allows for tiny borrowings of energy over incredibly short timescales, particle and antiparticle pairs can spontaneously pop into existence from the vacuum. They exist for a fleeting moment before annihilating each other and vanishing back into the energy of the field. It is a constant, frantic dance of creation and destruction happening all around us, in the space between stars and in the air between the atoms of your body. This isn't just a mathematical curiosity. We can observe its effects in something called the Casimir effect. Two metal plates placed extremely close together in a vacuum will be pushed together. Why? Because the space between the plates is so narrow that only certain wavelengths of virtual particles can appear there, while outside the plates all wavelengths can form. The greater pressure from outside forces the plates together, a physical push caused by the energy of nothingness. This vacuum energy has a profound and troubling connection to the cosmos. In Einstein's theory of gravity, empty space can possess its own energy density, a property he called the cosmological constant. Today, we see this energy at work as dark energy, the mysterious force driving the accelerated expansion of the universe. And here we encounter perhaps the greatest discrepancy in all of science, the cosmological constant problem. When physicists calculate how much energy the quantum vacuum should have, based on all the known particle fields and their virtual particles, the number they get is absurdly large. It should be 1 followed by 120 zeros times stronger than the dark energy we actually observe. If the calculated value were correct, the repulsive force of this vacuum energy would have been so immense that it would have torn the universe apart in its first instant, preventing any galaxy, star, or planet from ever forming. The fact that we exist means the observed value is almost zero, but not quite. Why is there this catastrophic mismatch between theory and observation? Is our math wrong? Is there some perfect, unknown cancellation mechanism that renders all this frantic quantum activity almost neutral? Or is it a clue that we are fundamentally misunderstanding the nature of empty space and gravity? The answer is critical because this tiny residue of vacuum energy, the dark energy we see, is now the dominant force shaping our cosmic destiny. It is deciding whether the universe will expand forever into a cold, dark, lonely end, or if some other unknown field will emerge to change its fate. The silent hum of the vacuum is not so silent after all. It is a whisper from the deepest level of reality, a whisper about how everything began and how it will all end. While the vacuum hums with phantom energy, a different kind of field might be responsible for the universe's greatest ghost. Most of the matter in the cosmos is invisible, a shadowy substance we call dark matter. We know it's there from its immense gravitational pull, which holds galaxies together and bends the path of light, but it has never been directly seen. One compelling theory suggests this cosmic phantom is made of axions, born from a field that fixes a strange imbalance in the heart of reality. This is the axion field. Its original purpose was to solve a deep puzzle in the laws governing nuclear forces, a problem known as the strong CP problem. In the quantum world of quarks and gluons, the equations allow for a certain kind of asymmetry that should make neutrons behave differently than their mirror images. Yet, in our universe, they do not. A neutron and its mirror reflection are identical. This perfect symmetry is a mystery. Why does nature respect this mirror symmetry when the math says it shouldn't have to? The axion field is the elegant fix. It acts as a cosmic referee, automatically adjusting the rules to enforce this symmetry, making the universe behave. But this solution came with a spectacular bonus. The same mechanism that solves the nuclear puzzle naturally produces a new, incredibly light particle, the axion. And these axions, produced in vast numbers in the early universe, are a perfect candidate for dark matter. Imagine this dark matter not as discrete particles colliding in the dark, but as a pervasive cosmic wave. Axions would be so light and so numerous that they would behave less like a gas and more like a fluid, a coherent oscillation of the axion field filling the entire cosmos. This is cold, wave-like dark matter. It does not emit, absorb, or reflect light, which is why it is completely invisible. It simply flows through everything, including you and the Earth, its only significant interaction being gravity. The hunt for this ghost is underway in laboratories around the world. Experiments like the Axion Dark Matter E-experiment, or ADMX, are listening for the axion's whisper. They use powerful magnets and ultra-sensitive detectors in an attempt to convert a passing axion into a faint microwave photon. It is like tuning a cosmic radio to a station that has been broadcasting since the beginning of time, waiting for the static to resolve into a signal. Finding the axion would be a double revelation. It would not only explain the missing 95% of the universe's matter, finally giving a face to dark matter, but it would also validate a beautiful solution to a fundamental problem in particle physics. It would show us that the fields shaping the cosmos are not just forces of construction, but also forces of balance, maintaining a delicate symmetry that allows our universe to exist as it does. Hidden in plain sight, the most familiar force in our lives is also the most mysterious. Gravity is not a force in the traditional sense, but a consequence of a hidden field that shapes the very stage of reality itself. This is Einstein's revolutionary idea, where the gravitational field is the curvature of spacetime. Mass and energy do not pull on each other across a distance. Instead, a massive object like the Sun warps the fabric of spacetime around it, like a heavy ball placed on a stretched rubber sheet. The planets orbit not because they are being pulled, but because they are following the curved geometry of this invisible landscape, rolling along the indentations created by the Sun's mass. This single theory redefined our cosmic understanding. It explains why light, which has no mass, still bends around massive galaxies, a phenomenon called gravitational lensing. It predicts the existence of black holes, objects so dense they carve a bottomless pit in spacetime from which not even light can escape. And it accounts for the subtle wobble in Mercury's orbit, a tiny discrepancy that Newton's gravity could not explain. Yet for all its power, general relativity is a classical theory describing a smooth, continuous field. The quantum world, however, is anything but smooth. To unite gravity with quantum mechanics, physicists propose that the gravitational field must also be quantized. This leads to the hypothetical graviton, a tiny packet of energy that would be the carrier of the gravitational force, just as the photon is for electromagnetism. Imagine the curvature of space-time not as a smooth slope, but as a subtle, granular texture made of countless infinitesimal gravitons. The challenge is monumental. Gravity is incredibly weak compared to the other forces. The energy required to probe the quantum realm of gravity is far beyond anything we can produce. Furthermore, the mathematics of a quantized gravitational field often produces nonsensical infinities that break our models. This conflict represents the final frontier in fundamental physics. Is space-time fundamentally smooth, or is it pixelated at the tiniest possible scale? The answer lies in the heart of a black hole or the first moment of the Big Bang, where both gravity and quantum effects reign supreme. Unlocking this secret would complete our picture of the universe's hidden fields, revealing the final rule in the cosmic code. Einstein's curved spacetime might not be the full picture. There is another, more twisted geometry hidden within the fabric of reality, a concept known as the torsion field. While general relativity describes mass and energy warping spacetime into curves and dips, torsion introduces a spinning, twisting motion to the mix. Imagine spacetime not just as a flexible sheet, but as a substance that can be wrenched like a towel being wrung out. This idea is not new. It was first developed mathematically nearly a century ago by the French mathematician Élie Cartan, who saw that Einstein's equations could be extended to include this rotational strain. In this richer geometry, every particle with intrinsic spin, a fundamental quantum property, would not only create a gravitational well but also a tiny whirlpool in spacetime. So what does this cosmic twisting explain? One of its most profound implications involves the mystery of dark matter. We see galaxies spinning so fast that their outer stars should be flung away into the void, yet they are held in place. The prevailing answer is a halo of invisible dark matter providing extra gravity, but torsion offers a different solution. The collective spin of billions of stars and particles within a galaxy could generate a significant torsion field throughout the galactic disk. This twisting of spacetime itself would produce an additional gravitational effect, one that perfectly mimics the extra pull we attribute to dark matter. In this view, there is no mysterious missing substance, only a previously overlooked property of spacetime, its inherent capacity to spin. This makes torsion a compelling alternative, a geometric fix for one of cosmology's biggest puzzles. The speculation goes even further. Some theoretical models propose a deep link between quantum spin and torsion, suggesting that the fundamental spinning of particles is directly coupled to the twisting of spacetime at the microscopic level. A handful of more radical thinkers have even wondered if this universal field of spin could, in some way, influence or interact with the complex networks of the brain, providing a physical basis for consciousness itself. While this remains highly speculative and far from mainstream science, it highlights the profound potential of this hidden field. Torsion suggests that the universe is not merely a stage of curves and slopes, but a dynamic medium alive with rotation, a hidden vortex within the vacuum that could rewrite our understanding of gravity itself. This hidden geometry of spacetime might not be the only force eluding our detection. Another phantom field could be hiding in plain sight by constantly changing its very nature. The chameleon field is a hypothetical scalar field whose mass is not fixed but shifts depending on its environment. In the dense heart of a planet or a laboratory, the chameleon field becomes incredibly heavy, effectively freezing in place and making its effects vanishingly small. But in the vast, empty voids between galaxies where matter is scarce, the field becomes extraordinarily light and long-range, its energy stretching across the cosmos and potentially pushing space itself apart. This remarkable ability to hide is its screening mechanism, a cosmic cloaking device that explains why we have not yet found it. Our most sensitive experiments on Earth are conducted in a relatively dense environment, surrounded by the mass of our planet and its atmosphere. Here, the chameleon is heavy and inactive, its subtle push completely masked. This very property makes it a prime candidate to explain dark energy, offering an alternative to Einstein's cosmological constant. Instead of a fixed energy inherent to the vacuum of space, the accelerated expansion of the universe could be driven by this dynamic, shape-shifting field. The chameleon is a key player in a class of theories known as modified gravity, such as F of R gravity. These theories propose that Einstein's general relativity, while brilliantly accurate, might be an approximation of a deeper truth. In F of R gravity, the way spacetime curves in response to mass is subtly altered, especially on the largest cosmic scales. The chameleon field naturally emerges from this modified geometry, acting as the agent that produces the extra repulsive force we attribute to dark energy. Imagine the universe as a vast, dark ocean. In the crowded coastal waters near galaxies, the chameleon field is like a dense, heavy fish hugging the seafloor, impossible to catch. But in the deep, empty abyss between galaxy clusters, it transforms into a vast, ethereal jellyfish, its gossamer threads filling the void and gently, inexorably pushing everything apart. The hunt for this cosmic chameleon involves looking for its effects where its screening might be imperfect. Scientists are designing intricate experiments using ultra-cold, tenuous clouds of atoms in vacuum chambers, creating regions of such low density that the field might finally reveal its light, long-range form. Others study the precise motions of stars within galaxies and the large-scale structure of the universe, searching for tiny discrepancies that a chameleon field would produce. Finding it would mean that dark energy is not a static feature of empty space, but a dynamic, living field that breathes with the structure of the cosmos itself. The universe may have a master volume control for all its forces. This is the Inflaton Field, a fundamental concept from string theory that governs the very strength of reality. In this framework, the intensity of every interaction, from the fierce grip of the strong nuclear force to the gentle pull of gravity, is not a fixed number. Instead, it is set by the value of this single, all-powerful field. The Inflaton's vacuum expectation value, its default setting in the emptiness of space, acts as a cosmic dial. One specific value for this field makes electromagnetism the strength we measure. Another sets the mass of an electron, and yet another determines how tightly quarks bind together. If this dial were turned even slightly, the constants of nature would change, and the universe as we know it would cease to exist. This field is intimately tied to one of string theory's most dramatic proposals, the existence of extra dimensions of space. Our reality is built upon the specific way these extra dimensions are folded up, or compactified, at scales far smaller than an atom. The size and shape of these hidden dimensions are described by fields called moduli, with the Inflaton being perhaps the most important of all. For our universe to be stable, these moduli fields, including the Inflaton, must be locked into their current values. This process is known as moduli stabilization. Without it, the constants of nature would wobble unpredictably, making chemistry and stable atoms impossible. In the fiery chaos of the very early universe, however, this stabilization might not have been complete. The Inflaton field could have been dynamic, rolling and oscillating as the cosmos cooled. During this epoch, the strength of all forces might have been wildly different. The electromagnetic force could have been stronger, gravity weaker, or vice versa. This presents a breathtaking possibility. The fundamental laws we consider immutable may have been forged in the first moments of time, crystallizing only when the Inflaton field finally settled into its modern, fixed value. What we perceive as the unchangeable rules of physics could be the frozen artifact of an ancient field finding its resting place. The search for evidence of this is incredibly subtle. If the Inflaton continued to shift even slightly after the Big Bang, it would have left an imprint on the cosmic microwave background or altered the relative weights of atoms. So far, our observations show the constants are constant, but the ghost of a dynamic dilaton, a universe still tuning its own laws, remains one of the most profound ideas in theoretical physics. The universe's expansion may not be driven by a static force, but by a living, breathing field that is slowly fading away. This is quintessence, a dynamic and evolving scalar field proposed as an alternative to Einstein's cosmological constant. Unlike a fixed energy baked into the vacuum, quintessence changes over time, its energy density and pressure shifting as the cosmos ages. Its behavior is defined by its equation of state, a simple ratio that compares its pressure to its energy density. For the cosmological constant, this value is fixed at exactly -1, producing a constant repulsive push. But for quintessence, this number can be different. It can be greater than -1, meaning its repulsive strength is not constant. It could be weakening, or it could even be growing stronger. This opens the door to cosmic fates far more dramatic than a slow, cold expansion. If the equation of state ever becomes more negative than -1, the quintessence field would enter a phantom regime. In this scenario, its repulsive force would grow without limit, eventually overcoming every binding force in the universe. This leads to the terrifying Big Rip. First, galaxy clusters would be torn apart, then individual galaxies. As the phantom energy intensifies, stars are ripped from their solar systems. In the final moments, planets, molecules, and even atoms themselves would be shredded by the accelerating fabric of space. The universe would end not with a whimper, but with a catastrophic tear in the very structure of reality. Of course, this is an extreme possibility. Current observations from distant supernova and the large-scale structure of the cosmos suggest that today's dark energy behaves very much like a cosmological constant. The data tightly constrains the equation of state to a value incredibly close to -1. Yet, there is still a little room for it to be slightly different, leaving a window open for a dynamic field like quintessence. One of its most attractive features is its potential to solve the coincidence problem. Why is the energy density of dark energy roughly comparable to the density of matter right now, in this specific epoch of cosmic history? If dark energy is a constant, this is a staggering cosmic coincidence. But if it is quintessence, a field that has been rolling down a potential energy hill for billions of years, its current value is not a coincidence at all. It is simply a phase in its long evolution, a moment where it naturally crosses paths with the dwindling density of matter. We are not living in a special time, but we are witnessing a predictable transition in the life of the cosmos. The hunt is on to see if this field is real. Does the equation of state show any tiny deviation from -1 over billions of years? Future telescopes, like the Roman Space Telescope and the Euclid Observatory, will map the history of cosmic expansion with unprecedented precision, looking for the telltale signature of a dying field. Is the force driving our universe apart an immutable feature of the void? Or is it the slow, final sigh of a dynamic field that has been with us since the beginning? The answer will decide our ultimate destiny. Space-time itself may be an illusion, a grand mirage emerging from a deeper, more fundamental layer of reality. This radical idea suggests that the seamless, continuous stage of the universe is not the starting point. Instead, it crystallizes out of a vast, buzzing network of quantum information, or from the interactions of more primitive quantum fields. At the heart of this emergence could be a theoretical construct known as the Inflaton Field, a field tied to the very concept of symmetry. In the hot, dense beginning, the universe was a state of perfect symmetry, a featureless soup where no distinct forces or dimensions existed. As the cosmos cooled, this symmetry broke, much the way liquid water freezing into structured ice creates distinct crystalline patterns. The Inflaton Field is the mathematical description of this transition, its changing value giving birth to the properties we now recognize as space and time. The geometry of space-time, its ability to curve and stretch, may not be fundamental but rather a collective behavior, an average effect of countless underlying quantum processes. This leads directly to one of the most profound concepts in modern physics, the holographic principle. It proposes that our three-dimensional universe of height, width, and depth plus time is actually a projection from a two-dimensional surface that surrounds it. All the information needed to describe every star, planet, and person in our cosmos could be encoded on this distant boundary, like a three-dimensional movie being projected from the surface of a giant sphere. In this view, the volume of space is an illusion. We are living inside a hologram, and the Inflaton Field could be the mediator that translates the information on the boundary into the geometric reality we experience within. The implications for quantum gravity are staggering. The infamous conflict between the smooth geometry of general relativity and the jittery quantum world simply vanishes if geometry is not fundamental. A black hole's paradox, where information seems to be lost forever, is resolved if all that information is safely stored on its event horizon, the two-dimensional surface from which our three-dimensional reality projects. The quest to prove this involves searching for the granularity of space-time. If space emerges from quantum bits, there should be a fundamental limit to how small distances can be, a pixelation of reality at the incredibly tiny Planck scale. Future experiments that study the timing of gamma rays from distant cosmic explosions might detect a subtle fuzziness, a hint that space-time is not perfectly smooth but is built from something deeper. We are left with a breathtaking possibility. The stage upon which the cosmic drama plays out is not a pre-existing given. It is the lead actor, born from a hidden symphony of information and symmetry, a cosmic hologram whose true nature is written on the edge of the visible world. Time itself could be a field waiting to be tuned. This is the speculative theory of the chronon field, a hidden medium that dictates the universal tempo, the rate at which cause leads to effect. If the gravitational field of general relativity shapes the stage of space, the chronon field would be the director controlling the speed of the play. Its local intensity would determine how fast or slow time flows, creating effects that go beyond Einstein's predictions. We already know from relativity that time slows near a massive object like a black hole, a phenomenon called gravitational time dilation. But a dynamic chronon field could produce its own time warps independent of gravity. Imagine regions of space where this field is inherently stronger, creating natural time slow zones, or weaker areas where clocks tick just a little faster for no apparent gravitational reason. This could manifest as subtle anomalies in the decay rates of unstable particles streaming through space. A muon, for instance, has a very precise half-life. If a beam of muons passed through a patch of space with an intensified chronon field, they might all decay just a fraction of a second slower than expected, as if time itself were stretching for them alone. The most dramatic possibility, however, involves closed time-like curves. In the bizarre geometry of general relativity, a path can theoretically loop back on itself in time, creating a bridge to the past. A stable chronon field with the right properties could, in theory, hold such a structure open, allowing for time travel into a previous moment. This immediately conjures the classic grandfather paradox. What happens if you travel back and prevent your own grandfather from meeting your grandmother? Your own existence would be erased, creating a logical inconsistency that seems to violate the fundamental laws of causality. Physics offers a few ways out. The Novikov self-consistency principle suggests that any actions taken by a time traveler were always part of history, so any attempt to create a paradox would inevitably fail through a bizarre chain of coincidences. Your gun would jam, or you would miss the shot, preserving the timeline you came from. Another, more radical idea is the many worlds interpretation, where each decision spawns a new universe. In this view, traveling to the past would not take you to your own history, but to a new, branching timeline, a parallel world where your actions have no consequence for the reality you left behind. Detecting the whispers of a chronon field is the work of extreme precision. Scientists analyze the arrival times of photons from distant gamma-ray bursts, looking for tiny, systematic delays that could indicate they passed through varying densities of this temporal field on their billion-year journey. Others monitor vast networks of atomic clocks, searching for synchronous, inexplicable drifts in their tick rates that might signal a wave of altered chronon intensity washing through the solar system. Finding such a field would force us to rewrite our understanding of reality's most fundamental rhythm, revealing that the arrow of time is not an immutable law, but the current setting of a cosmic dial. Every particle and every force may simply be data. This is the core of the information field theory, a radical proposition that the most fundamental substance of the universe is not energy or matter, but bits of information. Reality, in this view, is a cosmic computation, and the laws of physics are its unbreakable code. This idea pushes the holographic principle to its ultimate conclusion. We are not just living in a hologram projected from a distant surface. We are living inside a simulation where every star, every thought, and every law of nature is a line in an unimaginably complex program running on a computer of cosmic scale. The universe behaves like a giant quantum computer, processing information at every level. From the spin of an electron, a simple 1 or 0, to the chaotic dance of weather systems, everything can be described as the manipulation of data. Even the passage of time could be an illusion created by sequential processing cycles, a cosmic clock tick that updates the state of the entire system. This leads directly to the simulation hypothesis, the provocative suggestion that our entire cosmos is a design construct. If a future civilization could ever achieve a level of computing power vast enough to simulate a universe in perfect detail, complete with conscious beings inside it, then the odds are overwhelming that we are inside one of those simulations rather than the original, base reality. The implications are staggering. The speed of light could be the processor speed limit of the simulation, a maximum rate at which information can be updated across the cosmic grid. Quantum weirdness, like a particle being in two places at once until observed, could be the system's efficient rendering protocol, only calculating the precise details of a scene when someone is looking. Glitches in this reality, while incredibly rare, might be possible. Unexplained cosmic anomalies or particles behaving in statistically impossible ways could be seen as tiny bugs in the source code. Some scientists have even proposed tests looking for evidence of a fundamental pixelation of space-time or for conservation laws that are not perfectly symmetrical, hints of the underlying programming architecture. Metaphysically, this forces us to reconsider everything. If consciousness itself is just a complex pattern of information processing within the simulation, then what does that say about free will? Are our choices our own, or are they predetermined outputs of the algorithm? The information field theory does not necessarily make our lives less real, but it reframes reality itself. It suggests that the cosmos is not a collection of things, but a flowing, dynamic network of relationships, a story written in the most ancient language of all, the simple, binary language of existence and non-existence. We are not just made of stardust, but of something even more elemental, the pure data of creation. A crystal forming in a lab might be tapping into a cosmic memory. This is the heart of Rupert Sheldrake's theory of morphic fields, a radical idea that suggests the laws of nature are not fixed and eternal, but evolving habits. In this view, every natural system, from the simplest molecule to the most complex brain, is shaped by an invisible field that contains a collective memory of all that has come before. This is the morphic field, a non-physical pattern that guides the development and behavior of all things. When a new crystal forms for the first time, the theory states it must forge its own path. But once that structure exists, it creates a resonance that makes it easier for every subsequent crystal of the same type to form anywhere in the world. The morphic field for that crystal has been established, and through a process called morphic resonance, later crystals tap into that collective form, learning, in a sense, how to be themselves. This challenges the very bedrock of conventional science, which holds that a crystal's shape is determined solely by fixed laws of chemistry and physics. Sheldrake proposes instead that these laws are more like deep-seated routines, reinforced by repetition over time. The evidence cited for this is often behavioral. In one famous example, laboratory rats in one location learned to escape a new type of maze. According to the theory, as more rats mastered the maze, a morphic field for that specific solution was strengthened. Astonishingly, rats of the same breed in other labs with no physical connection then seemed to learn the same maze much more quickly, as if they were accessing a shared pool of knowledge. Supporters point to other mysteries, like how certain new chemical compounds suddenly become easier to crystallize in labs worldwide after the initial synthesis, as if the crystal's blueprint has been distributed on a field that transcends space. The mainstream scientific community remains deeply skeptical, dismissing morphic fields as pseudoscience. The primary criticism is the lack of a known physical mechanism. How does this information travel? How is it stored? The theory posits that resonance is not limited by time or space, a concept that conflicts sharply with our current understanding of physics and causality. For most scientists, the standard explanations of genetics for biology and quantum mechanics for chemistry are sufficient. The apparent evidence for morphic resonance, they argue, can be explained by poor experimental controls, selective reporting of data, or simple coincidence. Yet the theory persists, a provocative ghost at the feast of established knowledge. It asks a profound question. What if the universe is not a machine running on immutable laws, but a living, learning system where every action adds to a growing reservoir of form and memory? The morphic field remains one of science's great heresies, an idea that, if true, would mean we are all connected to the past in a far more intimate and mysterious way than we ever dreamed. That phantom energy of the vacuum is not just a theoretical curiosity. It is a real, measurable force, and it hints at a staggering possibility. The quantum vacuum is not empty. It is the zero-point field, a seething ocean of energy at the absolute lowest state possible. This is the ground state of the universe, and its energy is anything but zero. We can witness its power in a delicate laboratory experiment. Take two perfectly smooth, uncharged metal plates and place them a hair's width apart in a perfect vacuum. Astonishingly, they will pull toward each other. This is the Casimir effect. In the space between the plates, only certain wavelengths of the zero-point fluctuations can fit, like specific musical notes. But outside the plates, all wavelengths can exist. The greater pressure from the riot of virtual particles outside pushes the plates together. It is a physical force generated purely by the restless energy of nothingness. This observable effect has fueled a bold and controversial dream, the dream of free energy from the vacuum. If we could somehow tap this endless sea of quantum fluctuation, we would have a power source beyond any fossil fuel or nuclear reactor. The concept is simple in theory. Just as a windmill extracts energy from moving air, a hypothetical device could extract energy from the zero-point field. Science fiction loves this idea, portraying starships with vacuum engines that draw limitless power from the fabric of space itself. But the practical barriers are immense, rooted in the most fundamental laws of physics. The zero-point field is in its lowest energy state. You cannot draw energy from it in one place without paying a price elsewhere because of the law of energy conservation. Any device that tries to extract net energy would be like trying to siphon water from a perfectly level lake. You need a difference in energy, a slope, to make it flow. Some speculative proposals suggest using the Casimir effect itself, with microscopic gears that are ratcheted by the constant push and pull of virtual particles. Others look to rapidly changing materials that could alter the vacuum energy around them, creating a temporary energy gradient to exploit. Yet these remain firmly in the realm of theory, with most physicists deeply skeptical. The energy is there, humming in every cubic centimeter of space, but it is locked away by the universe's most unbreakable rules. The zero-point field is the ultimate temptation, a boundless power supply forever shimmering just beyond our grasp, a constant reminder of the untamed energy hidden within the void. A particle that lives its entire life beyond the light barrier defies our sense of cause and effect. This is the tachyon, a hypothetical entity born from a field with a property so strange it seems like a mathematical fantasy, imaginary mass. In our everyday world, an object with more mass requires more energy to accelerate, but for a tachyon, this relationship flips. According to the equations, its mass squared is a negative number, an imaginary value. To slow a tachyon down toward the speed of light, you would have to add immense energy. At rest, it would possess infinite energy, which is why it can never, ever travel slower than light. It is forever condemned to race through the cosmos at superluminal speeds. Its existence is tied to the tachyon field, a state of instability. Think of a pencil balanced perfectly on its tip. This is an unstable equilibrium, a false vacuum. The slightest disturbance, a quantum fluctuation, will cause it to fall and find its true, stable state lying on the table. The tachyon field represents that pencil standing on its tip. The field's value is perched at a precarious high-energy point, and the tachyon particle itself is the signal of that instability. The field's natural urge is to roll down its energy hill, a process called tachyon condensation, until it finds a stable minimum. This very mechanism is thought to be how other fields in the universe, like the Higgs, acquired their properties, a spontaneous symmetry breaking that gave rise to the laws we know. The most mind-bending consequence of tachyons is their assault on causality. If you could modulate a beam of tachyons to send a message, special relativity suggests that some observers would see that message arrive before it was sent. From their perspective, the effect would precede the cause, unraveling the logical sequence of time itself. This opens the door to paradoxes, like sending a signal to your own past with instructions to never build the transmitter in the first place. The universe, it seems, cannot tolerate such logical knots. This is the primary reason most physicists view tachyons not as real particles we might one day detect, but as mathematical red flags. Their appearance in a theory is often a sign that the researcher has defined the field around an unstable point, and that the system must evolve to a stable configuration where the tachyon disappears. It is the ghost in the machine, a warning that our equations are describing a reality that cannot persist. Yet the idea persists in the imagination, a shadowy suggestion that beyond the ultimate speed limit, an entire spectrum of physics might be waiting, forever closed off from our causally bound world. History once painted the universe as a silent, invisible ocean. This was the luminiferous ether, the absolute medium through which light waves were thought to ripple, much like sound waves through air. Its existence was a cornerstone of physics until two scientists in the late 19th century set out to prove it. Albert Michelson and Edward Morley designed an exquisitely sensitive instrument to detect the Earth's motion through this cosmic sea. They reasoned that as our planet orbited the Sun, it should create an ether wind, a current that would subtly change the speed of light depending on its direction. Their experiment was a masterpiece of precision, using beams of light split and reflected along perpendicular arms. If the ether was real, the beams would take slightly different times to return, creating a telltale interference pattern. The result was a shock that reverberated through the scientific world. They found nothing, no shift, no wind, no sign of the ether at all. The experiment was repeated with ever greater accuracy, always with the same null result. It was a death knell for the classical ether, and it paved the way for Einstein's radical new idea that light needs no medium and that the speed of light is a constant for all observers. The ether was banished from science, yet like a ghost it has never fully gone away. In modern physics, the concept has been resurrected in a new, more sophisticated form. Today's quantum ether is not a static material substance that things move through. It is the vacuum of space itself, reimagined as a dynamical, seething plasma of virtual particles and quantum fields. This is not an absolute reference frame, but a vibrant, energetic substrate from which space-time and matter may themselves emerge. In theories like loop quantum gravity, space-time is not smooth and continuous. It is woven from a fabric of tiny, discrete loops, a granular structure often called spin foam. This foaming, buzzing network of quantum relationships is a direct descendant of the ether concept, a fundamental medium whose properties give rise to the geometry we experience. Similarly, the idea of emergent gravity proposes that what we feel as gravity is not a fundamental force, but a collective phenomenon, an entropic force that arises from the statistical behavior of countless underlying microscopic degrees of freedom within this quantum ether. The modern ether is not a stage, but the lead actor. It is a dynamic entity whose fluctuations and interactions are the true source of reality's fabric. This is not your grandfather's ether, but a profound update, a hidden field whose quantum turbulence may ultimately explain the deepest nature of space and time. Consciousness could be a fundamental force of nature, as real as gravity or electromagnetism. This idea points to a noetic field, a hypothetical medium of mind that connects all consciousness across space and time. In this view, our brains are not generators of thought, but rather receivers, tuning into a vast, non-local field of information and awareness. This could explain phenomena that defy conventional biology, such as telepathy or remote viewing, where information seems to be exchanged without any known physical signals. The observer effect in quantum mechanics, where the act of measurement collapses a wave function, takes on a new dimension here. Perhaps it is not the physical apparatus, but the focused attention of consciousness itself, interacting with the noetic field, that brings potentiality into concrete reality. For decades, parapsychology has attempted to study these elusive effects under laboratory conditions. Experiments in Ganzfeld settings, where individuals attempt to receive information from distant senders, have occasionally produced statistically significant results that suggest something beyond chance is at work. Yet these studies are mired in controversy, criticized for methodological flaws and an inability to be consistently replicated. This touches upon the hard problem of consciousness, a puzzle that material science struggles to solve. How do the electrochemical processes in a lump of gray matter give rise to the vivid, subjective experience of the color red or the feeling of love? The noetic field offers an answer, proposing that consciousness is not produced by the brain, but is a primary component of the universe, with the brain acting as a filter or interpreter. So why does this idea remain on the fringes of accepted science? The primary obstacle is the lack of a detectable mechanism or a mathematical framework that can be tested with traditional instruments. Without a way to measure or quantify its influence, the noetic field falls outside the current paradigm of physics. For many scientists, it is not that the idea is wrong, but that it is currently untestable, placing it in the realm of philosophy rather than empirical science. Still, the possibility lingers, a profound whisper that the most intimate part of our existence, our own awareness, might be woven into the deepest fabric of the cosmos, connected to everything else in ways we are only beginning to sense. The dream of a single equation that describes everything has haunted physics for over a century. This is the quest for a unified field theory, a single master framework that would weave gravity, electromagnetism, and the nuclear forces into one elegant tapestry. Albert Einstein spent the last 30 years of his life chasing this vision, trying to show that electromagnetism and gravity were different expressions of a single cosmic field. He envisioned a universe where particles were not separate entities, but merely knots of tightly woven space-time. Despite his monumental genius, he failed. The mathematical tools and the deeper understanding of the nuclear forces were simply not there yet. The universe proved more complex than even Einstein could have imagined. The core of the problem is a fundamental clash between our two most successful theories. Quantum mechanics paints a world of probability and jittery particles, perfectly describing the three forces of the small, electromagnetism, and the strong and weak nuclear forces. General relativity, on the other hand, describes a universe of smooth, curving geometry, the realm of gravity and the very large. When you try to apply the quantum rules to gravity, the math explodes into infinities. It is like trying to write a love song with the vocabulary of a technical manual. The languages are fundamentally incompatible. Modern physics has launched two grand expeditions to bridge this divide. String theory proposes that the fundamental ingredients of reality are not point-like particles, but unimaginably tiny, vibrating loops of energy. An electron is not a dot, but a string vibrating at one specific frequency. A quark is the same string vibrating at a different note. In this symphony of strings, the force of gravity emerges naturally, carried by a particular vibration known as the graviton. The cost of this harmony, however, is immense. String theory requires extra dimensions of space, curled up into shapes so small we never perceive them. The specific geometry of these hidden dimensions would determine the laws of physics in our visible universe, making our reality just one possibility in a vast landscape of potential worlds. The rival approach, loop quantum gravity, takes a different path. It does not try to reinvent all of particles, but focuses squarely on quantizing spacetime itself. In this view, space is not smooth and continuous. It is woven from a fabric of tiny, discrete loops, a network of a billion threads. Picture the fabric of your shirt under a powerful microscope. What seems smooth to your eye is actually a grid of interwoven threads. Loop quantum gravity suggests spacetime has a similar granular structure at the smallest possible scale, the Planck length. Here, gravity emerges from the changing connections in this spin network. The implications of a successful theory of everything would be staggering. It would allow us to peer back to the very moment of the Big Bang, to a time when all forces were truly unified and the universe was smaller than an atom. We could understand what, if anything, came before that moment. We could finally know the true fate of the cosmos, whether it will expand forever, collapse back on itself, or transform into something entirely new. It would be the final chapter in our understanding of the universe's hidden fields, revealing the ultimate code from which all reality is written. Our cosmic map reveals a current flowing through the void. Galaxy clusters, the largest structures we can observe, are not drifting randomly. They appear to be streaming in a coherent direction at astonishing speeds, a mysterious phenomenon cosmologists call the dark flow. This is not the expansion of space itself, but a peculiar motion superimposed upon it, as if these colossal islands of matter are all being pulled toward a single, unseen horizon. The source of this pull cannot be within our observable universe, for its gravitational influence would be spread evenly across the sky. The dark flow points to something beyond the cosmic microwave background, the ultimate edge of our vision. The leading explanation invokes a bulk flow field, a vast gradient in the fabric of spacetime itself, created by an immense gravitational tide. What could be powerful enough to generate such a tide? One staggering possibility is that we are feeling the pull of other universes. In the multiverse scenario, our cosmos is one bubble in a frothing sea of infinite realities. A neighboring universe, impossibly close yet separated by higher dimensions, could exert a gravitational tug on everything in our own, creating this cosmic river. Alternatively, the cause might lie in the primordial structure of our own universe. If the Big Bang did not create a perfectly smooth cosmos, but one with a fundamental lopsidedness, a giant, pre-existing density fluctuation on a scale larger than we can see, its gravity would still be pulling everything toward it. The evidence for this ghostly current comes from a subtle anomaly in the oldest light we see. The cosmic microwave background has a known dipole, a hot spot, and a cold spot, which is mostly explained by our solar system's motion through the cosmos. But when you subtract that known motion, a residual dipole remains, an asymmetry that aligns perfectly with the direction of the dark flow. It is as if we are seeing the wake of our entire cosmic neighborhood moving through a hidden sea. The scientific debate is fierce. Skeptics argue the signal is at the very limit of our detection, a statistical fluke that will vanish with better data. They point to potential systematic errors in how we map the clusters and subtract foreground interference. But if the dark flow is real, its significance is profound. It would be our first empirical hint of a reality beyond our cosmic horizon, a glimpse into the multiverse or evidence that our universe is far grander and more uneven than we ever conceived. We are left to wonder if we are merely a leaf caught in a current flowing from a waterfall we cannot see. Deep within every living cell, a faint light flickers. This is the glow of biophotons, ultra-weak emissions of light that every living organism, from the simplest bacterium to the human body, constantly produces. These are not the bright flashes of fireflies, but an imperceptible whisper of photons, a subtle luminescence that hints at a hidden language of life. The theory of the biophoton field proposes that this light is not a random byproduct, but a fundamental medium for communication, a network that allows cells to talk to one another and coordinate their functions with astonishing coherence. Experiments have shown that DNA itself appears to be a primary source and receiver of these photon emissions. When a cell is stressed or damaged, the pattern of its light emission changes. Even more intriguingly, healthy cells placed near sick ones will sometimes alter their own light patterns, as if receiving a warning signal. This suggests that information about health, state, and function could be transmitted instantly through this field of light, far faster than chemical messengers could ever travel. This idea naturally pulls us into the strange world of quantum biology, a field that asks whether the bizarre rules of the quantum realm play a vital role in the messy, wet world of life. We already know that quantum effects are crucial in photosynthesis, allowing plants to transfer energy with near-perfect efficiency, and in bird navigation, where a quantum compass in their eyes may help them sense the Earth's magnetic field. The biophoton field could be another piece of this puzzle. Perhaps the coherence of this light, its ability to behave as a unified wave, helps synchronize processes across vast networks of cells, creating a unified state of health. What does this mean for our understanding of life and consciousness? If our cells are indeed connected by a web of light, then your body is not just a bag of chemicals, but a coherent, luminous being. Your sense of self, your vitality, could be deeply tied to the integrity and coherence of this inner light. Some researchers speculate that disruptions in this biophoton field could be the very root of disease, a breakdown in cellular communication that leads to dysfunction. The implications ripple out, suggesting that consciousness itself might not be locked inside our skulls, but could be an emergent property of this entire light-based network. While this field is still in its early stages of exploration, it forces us to reconsider the boundary between the physical and the energetic, and to wonder if the spark of life is quite literally a spark of light. Sound leaves its fingerprint in matter. When a violin bow draws a note across a metal plate sprinkled with fine sand, the grains do not scatter randomly. They dance, they organize themselves into intricate, pulsating patterns of stars, hexagons, and spirals, a direct translation of the unseen vibration into a visible, geometric form. This is the science of cymatics, the study of how sound makes shapes, and it points toward a profound possibility. A hidden cymatic field could be the universal translator between frequency and form, the medium through which vibration sculpts the physical world. The sand on the plate is a miniature model of a cosmic principle. Everything in the universe is in a state of vibration, from the orbit of an electron to the spin of a galaxy. Each vibration has its own unique frequency, and according to this idea, each frequency seeks to express itself as a pattern. The beautiful, symmetrical shapes that emerge in cymatics experiments are not arbitrary. They are the signature of the wave, the inevitable result of a specific frequency interacting with a malleable substance. This concept echoes one of the oldest ideas in human thought, the music of the spheres. Ancient philosophers like Pythagoras proposed that the planets in their orbits produced a celestial harmony, a symphony of pure tones inaudible to human ears. While we now know space is a vacuum that carries no sound, the metaphor is reborn in modern physics. The orbital frequencies of planets, the resonant frequencies of stars, and the background hum of the cosmos itself could be seen as a different kind of music, one that shapes reality not through audible sound, but through the fundamental vibrations of fields and forces. Could the large-scale structure of the universe bear the marks of this cosmic cymatics? Look at a galaxy. Its vast spiraling arms, tracing a perfect logarithmic spiral, are a stable, resonant pattern formed by density waves moving through the galactic disk. The distribution of galaxies across the cosmos, forming a vast cosmic web of filaments and voids, might also be a frozen record of primordial resonance, the standing waves from the Big Bang's first chords amplified across billions of light years. This naturally leads to the speculative link with sacred geometry, the belief that certain shapes hold profound universal significance. The patterns found in cymatics, the flower of life, the Sri Yantra, and the Fibonacci spiral seen in seashells and galaxies alike could all be different expressions of a common set of resonant frequencies embedded in the fabric of space. They are the preferred patterns, the forms that energy takes when it is allowed to settle into its most stable, harmonious state. The cymatic field, then, would be the hidden architect. It is the interface where the abstract world of frequency meets the concrete world of matter. When an atom forms, it is the resonance between electrons and the nucleus that determines its stable orbital shells. When a crystal grows, it is following the resonant pattern of its molecular bonds. From the microscopic to the cosmic, resonance might be the invisible hand that guides energy into the beautiful, complex, and ordered structures we see all around us. We are living in a universe that is not just expanding but singing, and every star and every stone is a unique physical note in its endless song. The void of space is not empty but full. Ancient philosophers once envisioned the cosmos as a plenum, a cosmic medium so packed with substance that true emptiness was impossible. This classical idea of a space brimming with an unseen essence finds a startling echo in modern physics, not as a solid body, but as a dynamic and all-pervading plenum field. It is a vision of reality where every point is saturated with potential, a fundamental fullness from which everything springs. This directly challenges our intuitive picture of a vacuum as a barren nothingness. In quantum field theory, the vacuum is a seething, active state, but it is still defined by fluctuations around an average of zero. The plenum field offers a more radical foundation, a background of such intense and constant activity that particles are not mere flickers in the dark, but persistent excitations in an already vibrant medium. Think of it as the difference between a quiet, empty room where a single voice occasionally speaks, and a roaring stadium where every possible cheer is already happening at once. You are simply tuning your attention to one specific sound. A powerful precursor to this idea was physicist Paul Dirac's concept of the Dirac sea. He mathematically described the vacuum as an infinite, unseen ocean of electrons occupying every possible negative energy state. A hole in this dense sea would behave like a particle with positive charge, which he identified as the positron, the electron's antimatter twin. This was a literal plenum, a cosmic ocean where particles are just bubbles in a deeper, more fundamental substance. The modern plenum field extends this further, suggesting a more abstract but all-encompassing substrate. If this field underlies everything, then the continuous creation and annihilation of virtual particles is not a process happening within an empty void, but a natural expression of the field's own restless energy. The universe is not hosting a show on a vacant stage. The stage itself is the performance. This perspective leads to a profound sense of interconnectedness. In a universe built upon a single, unified plenum, every particle, every force, is intrinsically linked because they are all just different vibrations or patterns within the same underlying field. You, the Earth, and the most distant star are not separate islands, but different whirlpools in the same cosmic river. This resonates strongly with the block universe theory in cosmology, where past, present, and future all exist simultaneously in a static, four-dimensional block. The plenum field could be the very substance of this block, the timeless, frozen medium within which the entire history of the cosmos is permanently etched. It is a holistic vision where separateness is an illusion, and the true nature of reality is an unbroken, dynamic wholeness, a single field of existence in which we are but temporary ripples. Every thought you have ever had might be permanently etched into the cosmos. This is the theory of the Akashic Field, a cosmic library said to contain a timeless record of every event, thought, and memory since the beginning of existence. In esoteric traditions like Theosophy and Anthroposophy, this field is known as the Akashic Records, a non-physical plane of information that acts as the universe's indelible memory. It is the ultimate book of life, and every soul is believed to write its own story upon its pages with every action and intention. This idea of a universal mind resonates with the holographic principle we explored earlier, where all information in our three-dimensional reality is stored on a two-dimensional boundary. The Akashic Field takes this a step further, proposing that consciousness itself is the medium through which this information is both recorded and accessed. It also finds a curious, speculative parallel with Rupert Sheldrake's morphic fields, where habits of nature are reinforced through resonance. While morphic fields deal with the forms and behaviors of biological systems, the Akashic Field encompasses the entire mental and historical experience of the cosmos. So why does this compelling concept remain firmly outside the halls of mainstream science? The core issue is testability. There is no known instrument or experiment that can detect or measure this field, and no mathematical model to predict its influence. For science, a hypothesis must be falsifiable, capable of being proven wrong. The Akashic Field, as described, operates in a realm that current physics cannot probe, making it a matter of metaphysical belief rather than empirical study. Yet, its enduring power lies in its profound metaphor. It suggests that no event is ever truly lost, and that every life is an essential sentence in a grand cosmic story. It offers a vision of ultimate interconnection, where your consciousness is not an isolated spark, but a ripple in a vast, intelligent field that remembers everything. It is the poetic answer to the haunting question of whether our lives matter in the grand scheme of things, proposing that they are forever woven into the very fabric of the universe. Our universe might have a hidden compass. For decades, the foundational principle of cosmology has been that the cosmos is isotropic, looking the same in every direction. But what if it is not? A new class of theories suggests the vacuum of space itself could be imbued with a direction, a built-in arrow created by a fundamental vector field. Unlike the scalar fields we have explored, which have only magnitude, a vector field also has a specific direction at every point in space. If such a field exists, it would pick out a preferred cosmic orientation, subtly breaking the rotational symmetry we have long taken for granted. This is the realm of anisotropic universe models where the fabric of reality has a faint cosmic grain. Such a field would leave its signature in the oldest light we can see. The cosmic microwave background should be almost perfectly uniform, a relic of the universe's hot, dense infancy. A vector field present at that time would have imprinted a specific pattern of hot and cold spots, a distinct anisotropy that our most powerful telescopes are now searching for. Another profound effect could be on the very laws of physics themselves. The fine structure constant, a number that governs the strength of electromagnetic interactions, is considered a fundamental constant. But if a vector field permeates space, its directional nature could cause this constant to vary ever so slightly depending on which way you look across the sky. The strength of light's interaction with matter would not be perfectly uniform throughout the cosmos, a finding that would shatter one of our most cherished assumptions. Specific theoretical frameworks give this idea mathematical form. In Einstein ether theory, a vector field, dubbed the ether, is woven directly into the gravitational fabric alongside the metric of spacetime. Its presence modifies the behavior of gravity in subtle ways, particularly in the early universe or near incredibly dense objects. Bumblebee gravity, another model, gets its name from a curious idea. According to folklore, aerodynamic calculations supposedly prove the bumblebee should not be able to fly, yet it does. Similarly, this theory explores how a vector field that spontaneously breaks Lorentz symmetry, the principle that the laws of physics are the same for all observers moving at constant velocity, could still result in a viable and consistent universe. The observational hunt for this cosmic direction is underway. Astronomers are meticulously analyzing the Planck satellite's map of the cosmic microwave background, looking for any statistical preference in the alignment of temperature fluctuations. Others are studying the light from distant quasars, searching for evidence that the fine structure constant was different billions of years ago when that light began its journey, and whether that difference correlates with a direction in space. Finding a confirmed signal would be a revolution. It would mean our universe is not a perfectly smooth and featureless expanse, but a structured medium with a built-in orientation. We would have to redraw our cosmic maps, adding a new fundamental axis to reality itself. The search for this ghostly arrow is a quest to see if the universe in its deepest foundations has a grain we must learn to read. Every particle in the universe is spinning. This intrinsic rotation is not like a planet turning in space. It is a fundamental quantum property as essential as mass or charge, and it might be the very thread from which the fabric of spacetime is woven. We are entering the domain of the spin field, a hidden architecture where geometry itself emerges from a vast network of these tiny, fundamental rotations. In the framework of loop quantum gravity, reality is not smooth and continuous. Space is quantized, broken into the tiniest possible grains. The mathematical tool used to describe this granular structure is a spin network, an abstract web of lines and nodes. Each line carries a label representing a quantum of area, and the connections between them define the geometry of space. The volume of a region is not a simple measurement, but a sum over all the nodes inside it. Your body right now occupies a specific volume because of the precise configuration of this invisible spin network underlying your position, but the cosmos is not static. How does this quantum geometry change and evolve? The answer lies in spin foam. Picture a spin network as a single frame in a movie, a snapshot of space at one instant. Spin foam is the entire film, a cascade of these networks evolving over time. It represents the history of space-time, a frothing, bubbling structure where the lines of the network branch and merge, creating a complex foam-like geometry. This dynamic foam is the quantum description of space-time itself, a tapestry of spinning connections. This radical perspective offers a stunning solution to the problem of cosmic singularities. In Einstein's general relativity, the Big Bang is a point of infinite density where the laws of physics break down. but in the spin foam approach there is no singularity. The quantum nature of geometry prevents space from being crushed into an infinitely small point. Instead, as we rewind the cosmic clock, the spin network becomes incredibly dense, but the quantized nature of area and volume sets a hard limit on how tightly it can be packed. The collapse reaches a maximum density and then rebounds. The Big Bang was not a creation from nothing, but a great bounce from a previous phase of universal contraction. Our entire cosmos could be the result of a prior universe that collapsed and then sprang back out again. This quantum transition elegantly avoids the mathematical nonsense of infinity, replacing the terrifying singularity with a physically plausible, though profoundly strange, event. We are left with a universe where the spin of an electron is not just a property of a particle, but a whisper of the deepest structure of reality, a single note in the symphony of a spinning, quantized cosmos. The phantom field is a specter haunting cosmology, a form of dark energy so potent it could unravel the universe at its seams. Its power is defined by a single, terrifying number in its equation of state. For the dark energy we currently observe, this value is very close to -1. But if a phantom field exists, this number would be less than -1. This small mathematical difference has catastrophic consequences, turning the gentle push of dark energy into an ever-strengthening, unstoppable force. The phantom field would possess negative kinetic energy, a property that causes its energy density to actually increase as the universe expands rather than dilute. This creates a runaway feedback loop of destruction. As the phantom energy grows, it accelerates the expansion. This accelerated expansion stretches space further, which allows the phantom energy to grow even more. The universe would begin to tear itself apart from the largest scales down to the smallest. First, the phantom energy would overcome the gravitational glue holding galaxy clusters together. These colossal structures would be flung into the ever-darkening void. Next, the gravitational bonds within individual galaxies would fail. Stars would be ripped from their orbits, sent flying alone into the expanding emptiness. Then, solar systems would be shredded. Finally, the force would turn inward. The phantom energy's repulsive force would grow so strong that it would exceed the very forces that hold matter together. Planets would be torn apart, the chemical bonds within molecules would snap. In the last fraction of a second, atomic nuclei would be shredded, and even the fabric of spacetime itself might be fractured. This is the Big Rip, a cosmic end of absolute disintegration. The theoretical viability of such a field is hotly debated, as it directly challenges the so-called energy conditions that are foundational to general relativity. These conditions, like the null energy condition, essentially state that energy cannot flow faster than light and that gravity should always be attractive. The phantom field violates these principles, allowing for exotic and seemingly impossible behavior. Current observations from supernova and the cosmic microwave background tightly constrain the equation of state, and for now, the data is consistent with a simple cosmological constant. The value remains tantalizingly close to -1, leaving only a tiny window for phantom energy to exist. Yet, that window remains open, a sliver of possibility for a universe destined for a far more violent end than a slow, cold freeze. The phantom field represents the ultimate limit of dark energy's power, a theoretical warning of a cosmos that could one day turn its expansive force inward, devouring itself from the inside out. A photon could have a secret mass. That idea alone challenges one of physics' most sacred principles, the gauge symmetry that keeps the electromagnetic force perfectly massless and infinite in range. But what if there is another way, a hidden field that grants mass without the cosmic drama of symmetry breaking? This is the Stuckelberg mechanism, an elegant and often overlooked alternative to the Higgs field. While the Higgs boson gives mass by breaking symmetry, the Stuckelberg field achieves the same end while perfectly preserving it. It works through a clever act of compensation. A massless particle like a photon has only two transverse polarization states, like a wave oscillating side to side. To become massive, a particle needs a third longitudinal state, a wave that oscillates forward and backward. The Stuckelberg field provides this extra degree of freedom, essentially donating its own identity to the photon to make it massive, all while keeping the underlying mathematical symmetry of the theory perfectly intact. It is a ghost that steps in to complete the picture without disturbing the frame. This mechanism is not just a mathematical curiosity. It becomes a powerful tool for theorizing about what lies beyond the standard model, particularly in the search for dark matter. One of the most compelling candidates is the dark photon, a hypothetical massive gauge boson that could be the carrier of a new, hidden force. In these theories, the dark photon acquires its mass not through a hidden Higgs field, but precisely through the Stuckelberg mechanism. This makes the model simpler and more elegant, avoiding the complexities of an entire new symmetry-breaking sector. The dark photon would be a massive, stealthy cousin to our own photon, interacting only very weakly with normal matter, which is why it has remained hidden for so long. It could be the particle that mediates interactions within the dark sector, the unseen world that makes up most of the universe's matter. The hunt for these massive photons is underway in laboratories around the globe. Experiments are designed to be exquisitely sensitive to the faintest whispers of such a particle. Some look for it directly by searching for a resonant reaction when normal photons are fired into a powerful magnetic field, a place where they might occasionally oscillate into their dark counterparts. Others search for it indirectly by looking for tiny discrepancies in the magnetic properties of subatomic particles like the muon, where a dark photon's influence would cause a measurable deviation from theoretical predictions. Finding a massive photon born from a Stuckelberg field would open a portal into a hidden universe, revealing a shadow force that has been woven into the cosmos all along, a silent partner to the light we see. A hidden symmetry could unite all the forces of nature. This is the promise of supergravity, a breathtaking framework that seeks to weave the force of gravity into the same tapestry as the electromagnetic and nuclear forces. It achieves this through a profound principle known as supersymmetry, a theoretical symmetry that connects the two fundamental classes of particles, fermions and bosons. Every particle we know would have a superpartner, a shadow twin. Fermions, the building blocks of matter like electrons and quarks, would have bosonic superpartners. Bosons, the force carriers like photons and gluons, would have fermionic superpartners. In this perfectly balanced cosmos, matter and force are two sides of the same coin. The graviton, the hypothetical quantum of gravity, is a boson. Its superpartner is the gravitino, a fermion. But there is another crucial player born from this unification, the graviphoton. This hypothetical particle emerges from the mixing of the gravitational field with other fundamental fields, specifically the electromagnetic field. Think of it as a cosmic hybrid, a single entity that embodies aspects of both gravity and electromagnetism. The graviphoton field would be the medium of this interaction, a hidden field that allows these two fundamental forces to communicate and transform into one another under specific high-energy conditions. This leads to the prediction of new, ultra-weak forces. While gravity pulls and electromagnetism pushes and pulls, the graviphoton could mediate a force that is neither, a subtle interaction that only becomes significant in realms of extreme density or energy, like the first moments after the Big Bang or the violent collisions of cosmic strings. For decades, supergravity was a leading candidate for a final theory of everything, a crucial step beyond string theory. Its most elegant version, 11-dimensional supergravity, paints a universe with 7 hidden, curled-up dimensions, a geometric structure from which all the laws of physics naturally emerge. The mathematics of this theory is uniquely beautiful, suggesting it might be the one true description of reality at its most fundamental level. The theory makes concrete predictions for particle physics, the most prominent being the existence of the entire spectrum of superpartner particles. At the Large Hadron Collider, scientists have been searching for these particles like the photino, the superpartner of the photon, or the squark, the superpartner of the quark. So far, the detectors have remained silent, revealing no signs of supersymmetry at the energy scales we have probed. This null result has been a profound puzzle, forcing theorists to reconsider whether supersymmetry is broken at a much higher energy or if nature chose a different path entirely. In cosmology, supergravity offers compelling solutions. The gravitino, for instance, is a prime candidate for dark matter, a stable, massive particle that could form the invisible scaffolding of the universe. The dynamics of the graviphoton field in the early cosmos could have seeded the primordial magnetic fields that stretch between galaxies, or influenced the phase transitions that shape the cosmos we see today. The silence of our experiments does not necessarily mean supergravity is wrong. It may mean we are still listening for the wrong notes, or that the symphony of unification plays at a scale far grander than we have yet witnessed. The dream of a single, unified field connecting the gravity of planets to the light from stars remains one of the most powerful and elegant quests in all of human thought. These ripples in spacetime are the voice of the tensor field. Unlike the scalar fields that fill space with a single value or the vector fields that point in a direction, a tensor field describes something far more complex, the dynamic geometry of spacetime itself. It is the mathematical language of gravity in Einstein's universe, a field that encodes how space stretches, compresses, and twists. When massive objects like black holes spiral toward a cataclysmic merger, their immense acceleration doesn't just create a gravitational pull, it literally shakes the fabric of reality, sending out waves of distortion that travel at the speed of light. These are gravitational waves, the direct prediction of the tensor field in motion. For a century, they were only a theoretical ghost until the morning of September 14, 2015. Two colossal laser interferometers, the Laser Interferometer Gravitational Wave Observatory, or LIGO, one in Louisiana and one in Washington state, registered a nearly identical chirp. It was a fleeting signal that lasted less than half a second, a cosmic thud that matched the precise waveform of two black holes, each about 30 times the mass of our Sun, colliding over 1 billion light-years away. The detectors work by splitting a laser beam down two 4-kilometer-long arms set at a perfect right angle. In the quiet vacuum of those tunnels, scientists measure the time it takes for the light to bounce back. A passing gravitational wave does not push things around. Instead, it subtly alters the geometry of space itself, momentarily making one arm infinitesimally longer and the other infinitesimally shorter. The laser beams, now out of sync, create an interference pattern that betrays the wave's passage. It was a distortion thousands of times smaller than the nucleus of an atom, yet we measured it. Since that first historic detection, LIGO and its European counterpart, Virgo, have listened to a growing chorus of cosmic crashes. They have heard the spiraling dance and final merger of more black holes, and in a landmark event, the collision of two neutron stars. That event was a multi-messenger masterpiece, as telescopes across the globe and in space saw the accompanying flash of gamma rays and the brilliant glow of heavy elements like gold and platinum forged in the cosmic fire. By studying the unique tremors of these waves, we are probing gravity in its most extreme regime, near the event horizons of black holes where spacetime is bent to its breaking point. We are testing whether Einstein's theory holds true under such duress, listening for any subtle deviation in the wave's ring-down that might hint at new physics. Could the echoes we detect one day reveal the presence of extraspatial dimensions, or the influence of another unknown field woven into the gravitational tensor? Each new chirp from the dark is a direct message from the tensor field, a ripple from a violent event that happened eons ago, now washing over our world and whispering the secrets of spacetime's true dynamic nature. Gravity may have a silent partner, a hidden field that whispers alongside the curvature of space-time. This is the world of scalar tensor theories, where the force we feel is a duet between Einstein's familiar tensor field and a subtle, all-pervading scalar field. In these models, gravity is not a solo act performed by the geometry of space. It is a collaboration with the scalar field acting as a cosmic volume knob that can fine-tune the strength of the gravitational force itself. The most famous of these is Brans-Dicke theory, developed in the 1960s as a compelling alternative to general relativity. Here, the gravitational constant, the big G we all learn in physics class, is not a constant at all. It becomes a dynamic variable, its value determined by this background scalar field. Imagine if the rules of attraction between every star and planet could slowly change over billions of years, growing slightly stronger or weaker as the cosmos evolves. That is the profound implication of this partnership. The scalar field's value could vary across space or drift over time, meaning the force of gravity in the early universe might have been different from what we measure today. This offers an elegant alternative to the cosmological constant for explaining dark energy. Perhaps the accelerated expansion of the cosmos is not driven by a fixed energy in the vacuum, but by the evolving dynamics of this scalar field, gently pushing the universe apart. Modern versions of this idea, like the complex framework of Horndeski theory, expand this concept into a vast landscape of possibilities. These theories allow for more intricate interactions between the scalar field and the geometry of spacetime, providing a rich toolkit for model building. They can be used to construct novel models of cosmic inflation, where a single scalar tensor field drives the universe's explosive birth and later seeds the formation of galaxies, all within one unified framework. Yet, for all their theoretical beauty, these ideas must survive the harsh light of observation. Our solar system becomes a precision laboratory for testing gravity. Exquisite measurements like the tracking of spacecraft orbits and the laser-ranging retroreflectors left on the Moon by Apollo astronauts tightly constrain how much a scalar field can meddle with gravity within our cosmic neighborhood. So far, Einstein's pure tensor description has passed every test with flying colors, forcing the scalar field in these theories to be incredibly faint, its influence heavily screened within dense regions like our solar system. But on the vast cosmic scale of the entire universe, the scalar field could still stretch its influence, its subtle push potentially explaining the dark energy we observe. The hunt now moves to cosmology. By studying the large-scale distribution of galaxies and the subtle patterns in the cosmic microwave background, astronomers are searching for the ghostly signature of a scalar field that has been shaping the cosmos since the very beginning. Is gravity truly a constant, unwavering force, or is it a dynamic dance, its strength guided by a hidden partner we are only now learning to sense? We have traveled from the cosmic molasses of the Higgs Field to the timeless records of the Akashic, exploring 30 different visions of the universe's invisible architecture. Each theory, from the well-tested to the wildly speculative, paints a picture of a reality that is profoundly strange and deeply interconnected. The empty space around you is not a void, but a vibrant plenum of quantum fields. The force of gravity may be a duet, not a solo. Your own consciousness might be a localized expression of a universal mind. This journey reveals that the solid, predictable world we experience is a magnificent illusion, a surface layer atop a hidden world of dynamic, whispering fields. They are the true authors of reality, sculpting everything from the mass of an atom to the ultimate fate of the cosmos. So we leave you with a final question. Which of these hidden realms captures your imagination the most? Is it the phantom energy tearing at the fabric of space, or the cosmic memory that records every thought? Let us know in the comments, and if you are hungry for more journeys to the edge of understanding, be sure to subscribe for our next deep dive into the mysteries of the cosmos.